Yes, sir.
So next we'll study uh, on representation of numbers. So we have seen that different filter characteristics, the implementation of different filters, and we have seen that filter coefficients plays a big role for getting some characteristics. It may be in spectral domain. So filter coefficients generally represents the poles and zeros to the system. Okay. And poles and zeros represents the frequencies at which there will be either gain or loss. So if the poles and zeros get changed, that means the frequency response will change. And at the same time, the poles and zero gets changed due to the change in the filter coefficient. Generally, these filter coefficients are stored in digital computer or digital system or digital software, a DSP processor, where some memory elements are used. So in those memory elements, these digital filter coefficients are stored. So if we cannot properly store the bacterial values of filter coefficients, so if the memory size is limited, okay, then obviously you have to truncate or you have to round up the filter coefficient. Suppose one filter coefficient is 0.5556, whatever it is, a six digit filter coefficients, but your computer is a 4 digit system. Okay. So obviously you have to uh, round up that six digit number to a 4 digit number. So in that case, the filter coefficients will change and it may affect the spectral characteristics of filter. Okay. So due to so what kind of effects are arised in those cases, that should be analyzed. So here some topics are there, that how what kind of effect is generated, that is called uh, quantization effect, okay, or round of effect or truncation effect, and then quantization effect. And also it is mm, related to the method how we described one numbers. It may be binary number, it may be and you know that is a fraction. We the filter coefficients are generally a fractional number. So how we represent those fraction in some particular number system. Okay. So here we will go through some brief discussion about this, because you have studied, you have some bit of idea about this. Okay. So uh, there are two kinds of number system. One is fixed point representation, another is floating point representation. Okay. So in fixed point representation, generally the sign bit or sign bit, the numbers contain sign bits and also the binary point. So in fixed point representation, binary point is placed in the extreme left of a register, okay, or extreme right of a register. That is, binary point is fixed, whereas in floating point representation uses a second register that designates the position of the binary points. Okay. So there are broadly two kind of representation. One is fixed point, another is floating point. Fixed point, binary point is positioned at the extreme left or right of a register. And in floating point, another separate register is used that designates the position of the binary point. So this is the broad definition of binary point representation. Okay, now let us discuss fixed point representation of numbers. Okay. You see that I am not going to the mathematical equation. It's simply any any number. Okay, you see that two examples are given. Let us say it is 123.45. Okay, and another number, and it is in decimal number. So in binary number, one example is there, that is 101.01. Okay. So how this is, what does this mean? That 123.45 is actually 1 into 10 to the power 2 plus 2 into 10 to the power n plus 3 into 10 to the power 0. Then this is the before the point, and after the point they are multiplied with the power of negative power of 10, that is at the corresponding points, decimal points. So 4 into 10 to the power minus 1 plus 5 into 10 to the power minus 2. Okay. So this can be equated with the equation that is given x, okay, as sum is equal to sum of this is the sum is equal to bi into r to the power minus I, okay, where bi represents the particular weight, okay, binary digit, and r is the radix or base. Okay, if it is decimal, then r is equal to 10. If it is binary, then r is equal to 2. Okay. If it is binary, then if it is decimal, then b range from 0 to n. Okay. B range from 0 to n, 0 to 9. Okay. So r, that is r minus 1. R is equal to 10, so 10 minus 1, 9. And if it is binary, then it is 0 to 1. Okay. B range from 0 to 1. So in this way, we represent the numbers, fixed point numbers. Okay. Now, there are some discussion about three cases. One is signed, one is signed number, okay, signed magnitude format. Another is ones complement, another is twos complement method. Okay. So let us see that in those representation, how we represent positive number. Okay. So positive number is represented with 0 at the beginning. Okay. So 0 point B1, B2 up to certain length. Okay. So, and negative numbers, negative number is represented by 1 at the beginning. Okay. So 0 represents the positive number at the beginning and 1 represents the negative number at the beginning. Okay. In case of sign magnitude form. So sign magnitude, it is 1 dot. So your number is say it is say your number is some point 0 point b1 b2 or 0.1111 kind of thing. So if it starts with 0, then it represents positive number. Okay, and if your number is 1 point b1 b2, in place of b1 b2 many bits may be there, that like 1110 whatever it is, so that time it represents the negative numbers. Okay, and in one's complement, how we get one's complement? First you have to write any number in terms of its corresponding positive sign magnitude format. Then you invert all the bits. Okay, all the bits. So you'll get one's complement format. Like your number is, say you want to represent uh, minus 0.11. Okay, minus 0.11. So you just invert all the bits. Okay, then it will be your your number is, say uh, mm, negative numbers in case of one's complement. Okay, your number is, say minus not minus, generally 0 or 1 are placed in front of all the bits. So first you take the signed positive sign magnitude in positive value, sign magnitude value. Okay. Then you invert all the bits. And in case of 2's complement, first you calculate the 1's complement, then you add by 1. Okay, then you add by 1. You can see here this equation 7.5.7. First you had calculated the 1's complement, like 1 dot b1 invert b2 inverts, like that. Actually 1 is the inversion of 0. Okay, that's why they are not written directly. They are directly written as 1 dot b1 bar b2 bar, that is inversion of all bits, then 1 is added. So this way 2's complement are calculated. Now let us see one example. Okay. At the bottom of the slide we can see that there are two numbers, 7 by 8 and minus 7 by 8. Okay. So represent these two numbers in sign magnitude, 2's complement and 1's complement format. Okay. So how we'll represent it? It is written, you can see that 7 by 8 is actually a positive number. Okay. So we can, this is a decimal number. How we can write 7 by 8? We can write as 7 by 8, we can write as 1 by 2 plus 1 by 4 plus 1 by 8. Okay, like 2 inverse plus 2 to the power minus 2 plus 2 to the power minus 3. Okay. So 7 by 8 is represented as 0.111. So this is a positive number 7 by 8, and it is same for all the formats. Okay. In 1's complement it is also 0.111, and 2's complement it is also 0.111. Okay. There is no change in case of positive number for all the cases: sign, magnitude, 1's complement and 2's complement. Then for negative value, that is minus 7 by 8, okay, we represent the sign magnitude representation of minus 7 by 8. First you get plus 7 by 8. Okay. First you get plus 7 by 8. So plus 7 by 8 is 0.111. Then in place of 0, you just write 1. Okay. 1.111. So you will get, in sign magnitude, it is 1.111. 0 represent positive sign magnitude for all. 0 represent positive for all cases. Then to 1's complement, to get it into 1's complement, what we have to do? First you get 7 by 8 plus 7 by 8. Then you invert all the bits. So plus 7 by 8 is 0.111. Then you invert all the bits, you will get 1.000. Okay. That is 1's complement. The number is 1.000. Okay. Then what will be in 2's complement? Can anybody tell?
Yes, sir. We add 1 to it. So 1001.
Yes, 1.001 is 2's complement by 7 by 8. Okay. Now, next I will not tell about this. If you find, you just go through the remaining of this slide. Okay. Then there are some how these numbers are represented. They are graphically shown. Okay, I'm not going it. Then now this last paragraph you study that in general, suppose if you want to multiply two fixed point numbers, okay, each of b bits, okay, then results what happened, we get 2b number of bits in length. So in fixed point arithmetic, the product is either truncated or rounded back to b bits. Means if your storage capacity is not of 2b bits, then you have to truncate the result to some lower order value. Or say if your storage capacity is of only b number of bits, then 2b bits should be truncated to b bits. So this will result some error, okay, due to the truncation of the filter coefficient. So this kind of effect is called round of errors. Okay? Round of errors. Now let us, so we have discussed the fixed point representation of numbers, where the binary point is located at the extreme left position, or extreme right position we have not seen, we have not discussed, but sometimes it is used. The extreme right bit positions may be used as fixed point one representation, but generally we keep it at the leftmost side. That is called fixed point representation. But another representation, that is floating point representation. And in fixed point, we have seen the problem is round off error. Okay. But in floating point, this can be overcome, that it, and also it cannot cover, be fixed point, it cannot cover very uh, large number, large valued number in fixed point. But in floating point representation, we can cover large valued numbers. So it has large dynamic range. So it is simple that how we represent floating point numbers, that we have, I have told you that there is some separate register used uh, to designate the binary points. Okay. So the binary points are initially at some part it is kept. At one, there are two parts in the number of floating points. Okay. One part contains the fraction value, another part contains the exponent part. Okay. The exponent part will tell you where the binary point should be. Okay. In the first part, you can say it is a magnitude part. Okay. There is some binary points. Binary point should be there, but where the binary point should be kept, that will be designated by the exponent part. That is another part of this register. So in the floating point, there are two parts you can see. One number is x. Okay. X is equal to m into 2 to the power e. 2 because it represents the binary number, and e represents exponent, that is power of the number, and m represents the mantissa. It is called mantissa. So the magnitude of this mantissa is actually in between half to 1. That is greater than equal to half, 0.5, and less than 1. In binary, half means 2 to the power minus 1. So 2 to the power minus 1 means, according to binary point, it is 0.1. 2 means 0.1. And if you add one more one after that, so it will be 0.11. So in that case, the number will be half plus 1 by 4. Okay. And you can add also another one, so it would be 0.111. So in that case, it will be 1 by 2 plus 1 by 4 plus 1 by 8. So whatever it is, it should not be equal to 1. Okay. If it would have been 1, then it would not start with 0 point something. It would be 1 point something else. But Mantissa always starts with 0.1 and value more than that. It may be positive or negative also. Okay. If it is negative number, then it would have been 1. So this 0 represents positive number, 0.1 represents, okay, plus 1 by 2, and 1.1 represents minus 1 by 2. Not actually, it is 1 in magnitude. 1.1 in Mantissa may be there, but that this the binary number before the binary point designates the sign of the Mantissa. Okay. So if it is 0.1, the Mantissa means 0.5 or half. Yes, half, 1 by 2. And if it is 1.1, that means it is minus half. So 1 represents negative Mantissa before the binary points, and before the binary points, if it is 0, then positive number. Before the binary point, if it is 1, then it is negative number. This is about the Mantissa part, whose magnitude should be half, more than or equal to half, to less than 1. Less than 1 because if it is equal to 1, then it would have been negative number. So we are not allowed to make it equal to 1. Okay. Then there is another part, that is exponent part. So that is called 2 to the power e. Okay? 2 to the power e. So that tell you where the binary point should be present. Okay? So let us discuss with some examples. One example is, say our number x1 is equal to 5. Okay, x1 is equal to 5. How we will represent this number into floating point system, floating point binary system? Okay. We know that the floating point has two parts. One is Mantissa, another is exponent part. Okay. Mantissa always, if it is positive number, it should start with 0. After that, some binary point 1, and remaining represents the magnitude of the number. What is the magnitude of the number? It is 5. So it is 5 in binary, it is 101. Okay. In fixed point, it is represented as 101.0. Okay. That is, the position of binary point is fixed. Here, binary, the magnitude may vary, but here, so we just get this magnitude 101 there in the Mantissa. So it becomes 0.101 in the Mantissa. Okay. So Mantissa we write 0.101, and if you keep it as same as 0.01, 0.101, then what number it would have been in fixed point? Can anybody tell?
Sir, 101.0.
0.101. In fixed point, how much it is? Only consider the number 0.101 in fixed point. In decimal, how much it is? So it is first 2 to the first number will be 2 to, you will be multiply the 2 to the power minus 1, then plus 0 plus 2 to the power minus 2. So it is 1 by 2 plus 1 by plus 0 plus 2 to the power minus 3. So it is 1 by 8. Okay. But actually in this floating point, we have to move, we have to shift this binary point. Okay. 0.101 is your not correct representation. So you have to shift this binary point 3 binary points right. Okay. So that means in the exponent we have to multiply with 2 into 2 to the power 3 into 2 to the power 3. Okay. So this exponent actually represents the position of the binary points. Where the positions of the binary points should be? It is actually 3 points, 3 binary point right. So 3 binary right movement should take place. So this point, binary point should go next to next to next, so that when you multiply this exponent with this number, it will become 101.0. Okay. So it is actually 5 in Mantissa, in floating point. Is it clear?
Yes, sir.
Okay. Then another number we take, that is 3 by 8. How will you represent this 3 by 8 in floating point? 3 by 8 in floating point using Mantissa and exponent. Okay. So in fixed point, 3 by 8 you can see is represented as 3 by 8 in fixed point can be represented as 0. It means after the binary point, all the digits should be multiplied with power of with 2 with power of corresponding decimal point, that is negative. So it is, say, if you multipy 0 into 2 to the power minus 1, then it is not actually 0. Then 3 by 8 is actually what? 1 by 4 plus 1 by 8. Okay. 0 plus 1 by 4 plus 1 by 8. 0, 3 by 8 is 0 plus 1 by 4 plus 1 by 8. So in fixed point, it is actually 0.011. Okay. 0.011 in fixed point. But in floating point, how we represent it? Floating point starts with 0.1. Okay. Because its condition is it is greater than equal to half and less than 1. So half means it is 0.1, okay, 0.1. So we have to consider this 0.1. Then another one we should write, because your fixed point is 0.011. So we have to consider 0.11. Then in the Mantissa, we write 0.11, and in the exponent part, we have to it is a separate register. In the exponent part, you have to mention the position of the binary point. Where the position of the binary point should be? So binary point should be moved left by 1 point. So actually your number is 0.011, but in Mantissa you have written 0.11. So this binary point should be moved left by 1 point. Okay. So it is written that binary point should be placed 1 point towards left to obtain 0.011. Okay. So hence the exponent should be 2 to the power minus 1. So 2 to the power of this value minus 1 represents movement of binary points by 1 unit left. If it is 2 to the power plus 1, then binary point movement would be 2 to the if the binary point movement is 1 point right, then it should be 2 to the power plus 1, like in the previous case. In this case, your Mantissa is 0.101, binary point movement should be 3 point right, so Mantissa should be 2 to the power plus 3. It represents shift of binary point, how much shift of binary point would be. So it is right movement, that's why it is plus 3. And here it is left movement, so it is minus, how much movement? Minus 1. So it is 2 to the power minus 1. Now this minus 1 is actually in minus 1, is that number should be written as also, how we write? It is written this way, 101. 1 represents negative, and so it is sign magnitude, nothing else. Sign magnitude. Okay. So it is 101. So E2 is 101. So your number 3 by 8 in floating point it is 0.11 and exponent is 101. Is it clear?
Yes, sir.
All of you have understood? Please raise your hand. Anybody else? Only 3 people raised hand. What the others doing? Okay. Okay, now another interesting thing, that suppose if you want to multiply these two numbers, okay, in floating point, the two numbers are, one number is not fraction, it is integer 5, another is fraction 3 by 8. So how we'll multiply? So these two numbers are written as x1 into x2, okay, that is x1 is 5 and x2 is 3 by 8. So in Mantissa format, the two numbers are m1, m2 into 2 to the power e1 plus e2. So m1 into represents the magnitude, okay, and 2 to the power some this thing is the exponent. So if you multiply these two, okay, then what happens? That first let us consider what happens to the power of the final numbers after multiplications. So 2 to the power e1 plus e2. e1 is 3 we have seen, and E2 is -1. Okay. So E1 is 3 plus 3, okay, in this number 5, and E2 is -1. That means -1, you have seen, we have discussed -1, how will represent it is 1, 0, 1. Okay, -1. -1 is 1, 0, 1, and E is 0, 1, 1. Okay. So these two should be added, but this should be added in 2's complement format. Okay. E1 plus E2 should be performed in 2's complement. So positive, there is no change in the positive number, because in 2's complement the numbers do not change. So it is 0, 1, 1. But -1, which was actually equal to 1, 0, 1, sign magnitude, this it should be converted into 2's complement. So in 2's complements, so -1, how we write that? So first you have to write +1. Okay, -1, how will represent in 2's complement? So first you have to write in +1, 0, 0, 1, then 2's complement, 1's complement, 1, 1, 0, then add 1. So it is 1, 1, 1. So then you add these two, you will get 0, 1, 0. Okay? And carry should be discarded. 0, 1, 0. So 3 minus 1 is 2. So it is plus 2. So it is, that's why it is coming 0, 1, 0. Okay? 2's complement. So this is about the exponent of the number. Now what about Mantissa? Mantissa was 0.11 and 0.101. Okay, 0.11 and 0.101. So if you then multiply this number, you will get 1111. And since there are point before these two numbers 101 and 11, so this number comprising of 3 digits, another number comprising of 2 digits, so whole number should be 3 plus 2, 5 digits. So that's why 1 0 should be placed before all these 4. So it is 0 1 1 1, and making, say you have the Mantissa bit format 6-bit only, a 6-bit format. So it is 0 0.11110, 6-bit format. Okay, 6-bit format. So after multiplying these two numbers, x1 and x2, in terms of Mantissa and this, okay, what we write as 0 0.011110 into 2 to the power 010, that is 2. Now you can shift the binary bit either left or right. Okay, so if you shift the binary bit to the right, okay, then you have to adjust the exponent part. Okay, so you are making the number higher. Okay, so you have to reduce the power of the two. So we have shifted this binary point right shift 1 bit. So you have to reduce this by this one, okay, -1. So now fixed point, okay, so fixed point it was actually 1.111, but in floating point it is 0.111 into 2 to the power 1. So this is one. Then how we do addition of floating points? Addition of floating points, actually both the exponents should be made of same power. That is the main criteria. So in one number, the exponent is 2 to the power 3. Okay, that is the case for 0.101. And for number 3 by 8, exponent is 2 to the power -1. First thing is that you have to make the exponent part, power of exponent same. So let us keep it the power of exponent same for these two number and say it is 2 to the power 3. So to make 2 to the power minus 1 to 2 to the power 3, 2 to the power 3, so we have to multiply with 2 to the power 4. So the number x2 is exponent, we want to keep it to 2 to the power 4. So you have to adjust the mantissa by this way. So there is 4 numbers should be added left to the numbers, or binary point should be moved left by 4 units. So you have to increase the power so that you can increase the power of this number to 2 to the power 4. So now 2 to the power 3 is in the exponent, and then you add m1 and m2. So it would become 0.101, 0, then 1, 1. So here actually one more 1 would be there. Is not written by mistake. Okay, this is actually this m1 and m2 should be added, so it becomes 0.101011. So this one would not be there, only 1 1. Let me correct it. Uh, here actually it is this one should not be there.
সিস্টেম চালিয়ে গেলাম আর স্যার বন্ধ করে দিয়ে চলে গেল।
So 0.101 would be added with 0.000011. So have you understood this? Yes or no?
Yes, sir.
Okay. I will upload this slide. Okay. So now time is over. Okay, you may leave now.